Okay, hello everyone. First, thanks for your interest in my talk, since you are even watching this video. And I'm again from Leiden University. Today I'm going to talk about the Horndeski dark energy. And the whole story starts from the Hubble tension, which you all might be quite familiar with right now. And this refers to a 5 sigma discrepancy between the H0, the Hubble constant values obtained by two separate ways. On one hand, we have our simple and nice lambda CDM model, which paired with the CMB observations constrain the H0 to be 67.4 with percent level precision. On the other hand, through the distance ladder approach, we can measure the expansion rate of the universe directly, locally, which gives 73-ish value. And now the discrepancy is reaching 5 sigma. This plot shows a time evolution of the Hubble tension. So we're having this discrepancy for more than 1 decade. And according to some recent developments, people at the Schultz group are becoming more and more confident of their measured value of 73. So it seems that at least in the near future, in a few years, we still have to live with the Hubble tension. The question now is, how do we live with the Hubble tension in our data sets? And it might not be a difficult question to answer in cosmology, since in the history of cosmology, we have learned to live with many, many things, starting from the discovery of the CMB, which turned out to be that the universe is much, much more homogeneous than the expectation of Big Bang theory. People invented inflation so that we can have a peace of mind with the scale invariant initial condition and the homogeneity of the universe. The same happens to the galaxy rotation curves and other observations such as structure formation, where in galaxies is rotating much faster than we expected by computing the mass from the visible matter. It turned out that both structure formation and the galaxy rotation requires that the gravitational potential be dominated by some dark matter that is invisible to our telescope. So we add dark matter and we learn to be comfortable with these observations. The same yet happened again 2 decades ago, where the observation of supernovas tells us that the expansion of the universe is accelerating. And we learned that we have to introduce a cosmological constant or dark energy to support that acceleration, which eventually gives us the lambda CDM. And now we're in a similar stage again. Observations tell us that there's a discrepancy between model expectation and the local observations called the Hubble tension. Right now, how can we live with the Hubble tension? There are many models proposed in regard of how we could live with this tension. And the one model that stands out is called early dark energy, because it makes us live with the tension comfortably together with the CMB datasets. And the idea is simple. We introduce some dark energy components near the matter radiation equality, which reduces the sun horizon and thus reduces our expected value of the radius from the Lux scattering surface to today the observer, which in the end would translate to a larger Hubble constant H0. And the feature of CMB is that it's one of the most precise measurements we've ever made in cosmology. So it constrains both background as well as the perturbations. So for introducing a dark component in CMB, we not only have to worry about the background, but also the perturbation consistently. And the way to go is by introducing this dark component as a scalar field, as we did for inflation, and as we did for dark energy. The simplest case, or EDE, is a canonical scalar field with a potential. And so far, the study of EDE has been focusing on the different shape of the potentials and its constraints from different combination of datasets, including the most recent CMB PR4. So the successful point of early dark energy is that it is compatible with the CMB, though there might be some issues with the more precise PR4 data. But at least it brings us a very important message. It's that CMB can accommodate one additional dark degree of freedom around recombination, which takes up nearly 10% of the universe's energy budget. Given the precision of CMB, this is a very non-trivial implication. And this gives us an idea whether we could promote the idea of EDE to a 1 degree of freedom and extension to gravity near CMB times. This is very similar to what people did in dark energy, where we promote the most simplest case quintessence to the full covariant theories covers dark energy as well as modified gravity. And the way to go is to use the Horndeski theories or generalized Galilean theories. They are the most general scalar tensor theory with the second-order equation of motion in four-dimensional space-time. And in some sense, it's also the simplest extension of gravity of GR because it adds one single degree of freedom, a scalar field. And it is general enough because for our case, because it includes both the generalized Brand-Sticky theories as well as KSS, kinetic gravity, braiding, Galileon, and many more models. So it is interesting to study Horndeski gravity within CMB times. But the question is, how do we do that? It is a very complicated set of theories with this kind of Lagrangian. So in case of dark energy, we're having the tools, mainly EFTCAMB and high class, to deal with the dark energy as a Horndeski field. But there's great limitation of these two codes when one wants to apply them to the study of early dark energy. As we have seen with many existing dark ADE models, oscillating fields is ubiquitous models within the EDE studies, but it is knownly very difficult to deal with within these two existing codes. This is because they rely on the EFT approach to solve for the perturbations, which solves for the dynamical variable delta phi over phi dot. And it is the variable or time shifts you need to go from an arbitrary gauge to the uniform phi gauge or the unitary gauge. This gauge is ill-defined when phi is not the time coordinate or when it's oscillating, namely. So this is the singularity. And as a simplest example, we can look at a canonical scalar field, which is perfectly stable with a quartic potential. And this is how class give you the delta phi solution. And once you convert that to pi, you get singularity every time the field oscillates and phi dot crosses 0, which is a big numerical instability if we want to use the same formalism as pi. And there are many ways to go. Probably the simplest way is to solve the delta phi equations directly instead of the phi field. And this is what we did in the new EFTCAMB, which will come in soon, later this year. It solved for the delta phi fields as well as the Einstein equations. It's stable when phi dot crosses 0. And because of it deals with delta phi, it can deal with general Horndeski theories starting from an arbitrary covariant Lagrangian. The cost to pay is that the expressions within the fields, the equations are much more complicated than the pi case because we now have the field redefinition redundancy. Luckily, all these are hidden in the code, and once compiled, they are hidden from the user. So to see the effect of Horndeski theories and using the new tools, let's flash through a very simple example, which we called Galilean early dark energy, or GEDE. It is a canonical scalar field with a potential term, adding one additional term, the Xbox phi or the Galilean term, characterized by one free parameter Kc. The background evolution is largely similar to early dark energy, where we're having an initial tracking solution given by this formula. And then when it evolves towards a saddle point in the phase space, it deviates from the tracking and goes to the fast rolling phase or the thawing phase of EDE. And in the end, it oscillates around the potential minima to redshift away its energy density. As we could already see from this formula, that Kc phi cannot be arbitrarily large, in that this term is within a square root. This gives us the stability criteria of Kc phi smaller than 5/12, but unbounded from below. And it turns out that this condition is enough to guarantee that the perturbation evolution is also stable. The most interesting feature of this additional Galilean term is called kinetic gravity braiding, where on the background it's characterized by one single parameter called alpha b, and it's with its effect in the first Friedmann equation. So with the positive alpha b, we see that with the same canonical scalar field energy density, we can have an even larger Hubble parameter. So a large H naught by reducing the sound horizon even more with a large H. And this is the case which we show on the right-hand side. So for the black line, it's the baseline where we fix FED and ZC for canonical scalar field. And the blue line is the same MG case, but with the MG parameter turned on. So it's the same peak, but different oscillations. And there's a third case where all parameters, we keep the scalar field the same as the MG case, just setting Kc to 0, showing that by turning off alpha b, we're having a much lower peak. This is the effect of kinetic braiding on the background side. On the perturbation side, the effect is much more complicated. It is dynamic around the horizon scale when alpha b is active, but on smaller scales, it's consistently attractive due to a larger than 1 modified gravity parameter mu, which gives you the effective Newtonian constant by mu times g. And mu, since mu is proportional to alpha b squared, it's always positive. So we're having an attractive fifth force on the small scales. And its effect is much more clear on the next slide, where we show the results. So we fit the model to data, including Planck PR4 plus Pantheon plus and baryon acoustic oscillations. And for the dashed lines, we additionally include large-scale structure observations from DES year 1. The first interesting feature is the value of omega b. So by including MG effect from GEDE, we are removing the necessity of increasing omega b, which is thought to be a common issue to all the early dark energy models. And the reason is twofold, mainly because we're having the increased growth from the MG effect on both intermediate and small scales to compensate for the effect of omega b, either baryon drag or diffusion damping. The next interesting thing about the model is that we are seeing a hint of MG or for the Galilean operator, in that we are seeing a non-zero peak in Kc phi around -2. And also it includes the Kc 0 or the canonical case at 95% credential level, so 2 sigma. Hint of MG effect. And furthermore, if we go one step further to use the nested sampling to compute the Bayes factor, you will see that the GED model is actually favored over the canonical EDE with the Bayes factor of 0.9, even though the GED model has one more parameter c. It is far from statistically significant, but it is enough to show that by going beyond canonical and adopting the Horndeski theories is very interesting in CMB times. And this probably concludes my talk today. And this is the take-home message. We're having a brand new code to resolve any arbitrary covariant Horndeski theory as well as oscillating or not. We're having MG effect in GED, which is favored by data. And also it turned out that MG effect can negate the need of increasing omega B in early dark energy models, which might be constrained by BBN or some similar observations. And thank you all for your attention.